Hey guys, welcome to day 18 of 100 Days of Code. Now today we're going to learn about some really exciting things. We're going to look deeper into Turtle graphics, starting to do things with graphics with the help of the Turtle module. And we're also going to be learning about Python tuples as well as looking deeper into importing modules in Python. By the end of today, we will have written some code that is capable of generating million-dollar pieces of artwork. So we're looking at a Damien Hirst, which sold for £1.275 million a little while ago. And we're going to be using Python Turtle to create a similarly beautiful dot spot painting, which could be randomized and create beautiful pieces of art like this one. Once you're ready, head over to the next lesson and let's get started. As I mentioned, in this section, we're going to be working heavily with the Python Turtle module. And as we've seen before, this Turtle module is essentially a way for us to be able to draw graphics onto the screen. And you can imagine it as just this little wandering turtle with a pen on its back, and everywhere it goes, it leaves a trail of line. So let's take a closer look at the Turtle graphics module. Now here, I've already created a brand new PyCharm project called Day18 Start, and I've created a blank main.py. Inside this project, we're going to import our turtle. So as you saw from previous lessons, we can import the turtle module and get hold of the turtle class by simply saying from the turtle module, import the turtle class with the capital T. And now we can work with that class, and we're going to use it to create a new turtle object. Let's call it Timmy the Turtle. And this is going to be created from the turtle class. So this is going to be a new turtle object saved inside this variable. Now, when we actually run our project, you'll see a brief flash of a window and then it will disappear. In order for that window to stay where it is and only exit when we actually click on the window, we have to create another object, which we'll call our screen. And this comes from the Turtle module as well, and it's a class called screen. We also have to import that if we want to use it. So now that we've got hold of the screen, we can use one of the functions called exit on click. So this way, when we run our code, we can see our turtle show up in the middle as this little arrow, and our window won't disappear until we click on it. That's what exit on click does. So we need to keep this bit of the code at the very bottom. It has to happen after we've done all the stuff with Turtle. So I'm going to move it to the bottom of the file. Now here's a question. How do I know how to do that? Is it because I am super experienced and I remember everything off the top of my head? No. Is it because I'm super clever and I can just work things out? No, that's definitely not the answer. The way that programmers go about figuring out how to use these modules or packages is through the use of documentation. So let's take a look at the Turtle graphics documentation. And this is what the documentation looks like. It's a very, very long document that goes through all of the things that you can do with this module. Now, if we scroll down, you've got a contents page here, and you can see the various things you can do with the turtle. Control its motion, or control the pen, or change its visibility or appearance. Now, let's take a look at this shape function. And you can see the documentation explains to us that this particular function will set the turtle's shape to one with a given name. And we can choose from the various shapes, including arrow, turtle, circle, square, triangle, and classic. So let's use this knowledge and change Timmy the Turtle to have a different shape. So inside here, we can put any of those strings. So I'm going to change it to a turtle shape. This way, when I run my code, you can see an actual turtle appear on the screen. It just makes it a little bit easier to visualize what's going on with this module. Now, of course, you can change it to any of the other ones, test it out and see if it works. In an ideal world, you would read through the entire documentation of a module before you start using it. But of course, in the real world, we all know that that's not quite possible. Very often, you'll need the help of Stack Overflow. For example, if we wanted to look at turtle graphics and we wanted to change the shape of the turtle, then you can see that when you actually search for this inside the Stack Overflow search bar, your results are not very relevant. But if I put the same query into google.com and at the end I tag on the keyword Stack Overflow, we get results that are a lot more relevant. So if we take a look at this post, you can see that it's starting to talk about this shape method. And down here, this answer even links to the relevant part of the documentation, which we've already seen previously, this shape method. The idea is that you might need to Google around to see how to achieve a certain thing you want to do. And then once you've seen some of the methods that they mention in the answers, then go to the documentation and read up on it in order to actually understand what it does and how to use it. Coming back to our turtle, what if we wanted to change the color of the turtle? Well, this should be quite easy. We can see that in the color control section, we can use this color method to set the pen color and fill color. So for example, we could say Timmy the turtle dot color, and we can put in a string here like red. So now when I run my code, you can see that my turtle, Timmy, is now red instead of the previous default color of black. Now, how do I know which colors I can use other than the ones shown in the example, red or green? Well, it says that when we want to change the color using a color string or an RGB color, then it accepts inputs as in pen color. So it basically says it's using this method to set the color. And this method gets the color from a TK color specification string. So let's Google and see what that is. If we click on the first link, you can see it takes us to the strings, and we've got a whole bunch of names and their corresponding RGB values. So what is this TK exactly? TK is short for the module tkinter, which is the TK interface. And this is one of the ways that you can use Python to create a graphical user interface, which is also known as a GUI. If you think back to the beginning of computer history, if you think about the Apple Lisa 1, that was the first computer that had a graphical user interface where it had a mouse and you can point and click. And this was huge back in the day. But before then, we had text interfaces like MS-DOS or like our console when we're using Python. The text interfaces accept text commands, and the graphical user interfaces can show images and allows you to click and drag and do all of those things by looking instead of just typing commands. And tkinter is what the Turtle module actually relies on under the hood to create these graphics, like our turtle showing up here. So now that we've seen where these names come from, a much easier way of using these colors is through a page where they have all been rendered on screen. So in the course resources, we link to this page where you can see all the colors next to their names, and you can pick and choose whichever one you want. Have a go at changing the color of the turtle by using one of these colors that you see on screen. Now that we've seen how we can create a new turtle and change its appearance, it's time to look at how we can make it do certain things. In the documentation, you can see there's a whole bunch of things you can do in terms of moving and drawing. A very simple one would be to move it forwards or to move it backwards. So we can tell it to move forwards by 100 paces. And when we rerun the code, this is what we see. So we can get it to move forwards, move backwards, and also move left and right. So here, the input that it takes is an angle, a number, between 0 and 360 to tell it what angle to turn right or to turn left. For example, currently our turtle is facing east. So if we want it to face south, then we have to get it to turn right by 90 degrees. So we can say Timmy the Turtle dot right, and then we put 90 in here. And that's what it looks like. In the upcoming lessons, we've got a whole bunch of turtle challenges for you. That's going to test not only your knowledge of programming that you've learned so far, but also how well you can read and understand documentation. This is a key skill to acquire as a seasoned developer. Because after all, we can't always rely on other people telling us what to do. We have to be able to get it from the source. So make sure that you've got the documentation pulled up and have a glance through it. Then you can head over to the next lesson and start tackling some of these challenges. Now remember that some of these challenges can be quite a bit of a struggle, but keep in mind that the struggle is good. The more that you struggle, the stronger you get. I'll see you on the next lesson. Alright, now the first turtle challenge I've got for you is pretty easy. It's kind of like doing your stretches before we get started with the proper workout. So in this challenge, you're going to be using Turtle to draw a square. It's going to be a simple 100 by 100 square, and it doesn't matter where it is on the screen. As long as you can get it to draw this, then consider yourself successful. Pause the video, have a read through the documentation, have a think about the challenge, and go ahead and complete it. Alright, so I'm going to comment out the previous lines of code, other than the line where we created our Timmy the Turtle. Now to draw a square is pretty simple. All we have to do is to get it to go forwards by 100 paces, and then we turn left or turn right by 90 degrees, and then we get it to repeat this process one time for each of the sides. And when we run the code now, you can see it draws a simple square. Now, of course, because we're programmers and we're lazy and we don't like looking at repeated code, a much simpler way of doing this is to simply create a for loop, and we're going to use the range operator to say that this loop should run 4 times, and then let's indent these 2 lines of code, and now it will do exactly the same as before, but this time we've only had to write 3 lines of code instead of a million. This is probably the best solution, but I will also take this solution because after all, we're just doing the warm-up, right? Now, while doing that exercise, you might have realized that it's actually really painful to keep calling our object Timmy the Turtle with such a long name. But now that we've written it in so many lines, especially if you created this version of the code, it's actually quite painful to go through each of them and change its name. Remember, in PyCharm, we have a really simple way of changing the name of a variable or a function, basically anything that we've named ourselves. All we have to do is right-click on the name, refactor, and rename, and we can change it to something really simple, like, how about Tim? Now we've drastically made our code look a lot simpler just by doing that one thing. I'll try to remind you of some of these shortcuts as we go along, but once you're ready, head over to the next challenge. So we're importing the Turtle module in order to use it in our code. So I want to spend a few minutes just quickly talking about all the ways that we can import modules. So we've already seen the basic import, and it's very simple. We have the keyword import, and then we have the module name that we want to import. So if we had just imported our Turtle module with the simple import, then in order to create a new Turtle, we would have to say the module name and then the name of the class. And we would create a new Turtle like this. Now, this is perfectly fine, but it would make it so much more convenient if we were using that Turtle class a lot to write our code like this. This way, we don't have to keep writing turtle.turtle or turtle. Whatever else it is that we want to import. And this code is, again, pretty simple. We have the keyword from, we have the keyword import, we have the module name, and also the thing in the module that we want to import. As you've seen, with this kind of syntax, we can simply write And this means that if we were creating a lot of turtles, let's say instead of just creating Tim, we also created Tom and Terry, then we don't have to keep writing turtle dot turtle turtle dot turtle every single time. So this from import is really helpful if you're going to use this thing that you're importing a lot and you don't want to keep writing the name of the module in front of it. Now you can actually go one step further. Instead of saying just from turtle import whatever it is you want, you can actually import everything by using the asterisk. Now you can use everything that's in that module as if it were in the current file. And this has advantages as well as disadvantages, because it can make it really hard to see where each of these classes or methods come from. So for example, if I just wrote forward, you can see I can do this, but it's really confusing to just see this method somewhere in isolation, because it's like, well, what is moving forward? What's actually happening? Where does this come from? And it's more obvious when you import a module like random. So from random, import everything. And then somewhere else in our code, we might just write something like choice. And this is a method from random where we can pick a random item from a sequence like a list. Now, this code works, but it's really confusing. Like, how is this choice working? Where does it come from? Which module enables this capability? Instead, we just have the method whack right in our code, and it's very confusing as to its origins. So amongst the Python community, it's very unusual that you'll see good code written like this. I want you to know what it does because you might come across it in the wild, just so you understand what it's actually doing, but I want you to try and avoid writing code like this. Instead, if you're using something from a module many times, so more than 3 times, then you can think about using this from import. But if you're only using it once or twice, then just import the whole module and write out this turtle.turtle so that you can see that this module is the one that contains this class, and that is imported, and we're using it to create this object. It's just a lot more expressive in terms of the code. Now, the final thing I want to show you, which is quite a useful thing, is how to alias modules. So for example, we can import our turtle as T. So what this does is we import from the turtle module and we give that module an alias name, so a name that we define. And what this means is that if you were to create your new object from the module turtle, instead of writing out turtle every single time, you can just write T. And it will represent the entire module. So sometimes you'll have modules which are really, really long. So it could have a really long name and you don't want to type it out every single time. So you give it an alias name and it will be exactly the same as referring to the entire name of the module. And you can create a turtle like this. Now, even though we've been writing import, there are some modules that you can't just import, right? So for example, if I wanted to import the heroes module, which is something that I can use to generate hero names like Decepticon or Leopardon or Ascutronics, then I can use one of the functions that's in that module, heroes, called generate. But if I just go into my code and I straight up try to import this module, which is called heroes, then you can see I get an error. And the error says there's no module named heroes. Why is it that I can't do this, but I can import turtle? Well, the reason is because turtle is a module that's packaged with the Python standard library. And this is a small library of code which contains just the basics to get you started, like a core set when you buy a board game, or like the basic track pieces when you buy a set of Hot Wheels. So you can imagine this library of code as like a family library, easily accessible, but very small. Now, if we wanted to access the whole world of Python modules and packages, then we need to go to a much bigger library. And that is, of course, the Python packages, which are hosted on the internet and we can install into our project as and when we need them. So this way, our final project doesn't become gigantic because we've got all of the modules loaded into it from the internet. Instead, we only plug and play whatever it is we need. So PyCharm is actually already smart enough to know that I probably want a module that I haven't installed. And you can see that as soon as I click on this error with the red underline, I get a red light bulb over here. And if I click on it, it gives me the prompt to install this package called Heroes. And once it's done, then we can actually tap into this module and we can say heroes.gen. And this is going to generate us a new hero name. So let's go ahead and run our code. And you can see we've got a name called Galvatron, which is not bad actually. So it's important to remember that when you try to import something that hasn't been installed, like this villains package, then when you try to run the code, you'll get an error that says no module named villains. And this should prompt you to think, maybe that module is not a part of the Python standard library like Turtle, and I actually have to install it. Just remember that before you can import a module, sometimes if it's not bundled with the Python standard library, then you might have to install it. All right, onwards to the next Turtle challenge. So this one is going to be a little bit more intensive, but still a bit of a warm-up. So we're just going to go for a light jog and we're going to draw a dashed line. You're going to get your turtle to draw a line like this, where it's going to draw a line for 10 paces and then a gap of 10 paces and then a solid line for 10 paces again. And it's going to repeat this until it does this 50 times. The actual length of the line doesn't really matter. The actual length of each of the sections doesn't really matter. What's really important is you're able to get this alternating draw, no draw thing going on. To complete this challenge, you're going to need to look through the documentation and maybe also use the help of Google or Stack Overflow and figure out how you can get this behavior to happen. Have a think about it and pause the video and complete the challenge. All right, so if we look through the table of contents here, we can see that the thing that controls the pen is in this section. We can control its drawing, color, filling, and more. Now, if we look at the drawing control, you can see we can get it to pen down and pen up. When we pull the pen down, that means the pen is on the paper and it's gonna make a mark. But when the pen is pulled up, then there's going to be no drawing happening when our turtle is moving. That means we can write some sort of loop, right? Where we get our turtle to move forwards by 10 paces. And then we can get this to pull the pen up. And what this is going to do is allow us to move forwards without drawing. So now while the pen is held up, we're going to go forwards once more, another 10 paces. This is going to draw the blank. And then finally, we're going to go ahead and put the pen down again. So now all we need is for these 4 steps to repeat 15 times. So we can write a for loop and then create a range that goes from 0 to 15. And then once we indent this block inside the for loop and run our code, then you can see it draw our dashed line. Did you manage to get this solution? Did you manage to find the relevant part of the documentation to be able to pull the pen up and put the pen down? Or did you simply change your code so that it drew black and then it drew white? All of these solutions would work, but what I really wanted you to do is to dig through the documentation and find the parts which will help you to achieve your goals. Head over to the next lesson and I've got another slightly harder challenge for you. All right, so the next challenge gets a little bit harder. It's like we're doing our sit-ups now. In this challenge, you're going to be drawing a triangle, square, pentagon, hexagon, heptagon, octagon, nonagon, and decagon. So from 3-sided shape to 10-sided shape. And each of those shapes is going to be drawn with a random color. And each of the sides are going to be 100 in terms of length. And the final outcome should look something like this. All of these shapes overlaid on each other and drawn out in sequence. So you'll have to think a little bit about this, because we know that a square has 90-degree angles. So we could get our robot to go forwards and then turn right 90 degrees and then go forwards again. But what about a pentagon? Well, a pentagon, each of the corners has a 72-degree angle. So what's the actual relationship? How can we work this out? Well, we know that to turn a full circle, it's 360 degrees. So the way you work out the angle of each of these shapes is by dividing 360 by the number of sides. So 360 divided by 5 is 72. So each of the corners is 72 degrees. Using this knowledge and what you've learned about Turtle, go ahead and see if you can complete this challenge. Pause the video now and give it a go. Alright, so I'm going to delete the previous code and we're going to write the code that's going to draw all of these shapes. The first thing I want to do is I want to put down that equation. So we know that if we have 360 degrees divided by the number of sides, then we get the angle, right? So let's save that into a variable called angle. And then all we have to do is to get our robot to go forwards by 100, we said, and then to get it to turn right. And the angle that it's going to turn right by is the one that we defined at the top there. So then we just need this to be repeated for as many times as we have number of sides. So we could create a for loop, for example. And the range is going to take into account the number of sides. So now if the number of sides is equal to, let's say 5, let's say we're trying to draw a pentagon, then this would be the code. So let's shift that along. And now if we go ahead and run this code, you can see it draws us a pentagon, a 5-sided shape. So how can we get this loop to run for the different sides? How can we get it to go from a 3-sided shape, a triangle, all the way to a 10-sided shape, a decagon? To do this, instead of setting the number of sides statically like this, why don't we create a function? Let's call it drawShape. And this function is going to take the number of sides that this shape has as an input. And then the rest of this code can be indented inside the function. And it probably makes sense to only calculate the angle once when we need to draw the shape, because for the given number of sides, that angle is going to be the same across the entire shape. For example, if it was a square, we're going to go from 1 to 4, drawing this 4 times. So now later on we can define another for loop, and this for loop is going to go through all of the different number of sides that we need. So we know that we need a range between 3 and 10, right? As we loop through this range, this shape side n is going to take on the value depending on where we are in the range. So when we're first drawing this, we're going to draw a triangle with 3 sides. So then we can pass this shape side n into our drawShape function, and that should go from 3 to 10. So let's run our code and see it draw our triangle first, and then our square, and then it just keeps on going until it draws all of the shapes that we need. Now, the very last part of the challenge is to make each of the lines a different random color. So how can we do this? So of course, we're going to go to our good friend Google, and we're going to search for the turtle colors in Python. I first tried to Google this without the Python, and I got the different colors of various turtles. which was really fascinating, but that's not quite what I wanted. So if we take a look at the first link, this comes from a website called Trinket, and it has this interactive color palette where you can select one of these colors that you like, and then you'll get the turtle name, which then you can copy and paste into maybe a list. Let's call it colors. And you can put as many colors into this palette as you want, and you can make it as extensive or as short as you want it to be. So here's a list that I created earlier. And now if we go ahead and set our turtle's color, so let's go ahead and get Tim and set his color to a random color from this list, which we know to be as simple as simply importing the random module, and then we can get hold of the random module.choice, and then inside that method we can pass in our list of colors so that it picks a random color from that list. So now let's run it again, and you can see each time the shape is being drawn, it's picking a random color from our list of colors. So there you have it. That's the solution to this challenge. And this was a little bit more challenging, I would say, because we're doing functions and loops, and you had to get hold of some colors, and you had to figure all of that out. But hopefully you've managed just fine, and you're ready to move on to the next challenge. Now, our next challenge is our press up. And this challenge is going to require you to draw a random walk. Well, it's basically your turtle making random movements north, east, south, or west each time it progresses by the same distance, but it can at any point choose which direction it wants to go out of the four. And also you can see we've kept the color palette from the previous challenge, and I've just applied it to the random walk so that each time it walks, it's going to pick a different color. Now, this random walk is something that's used often in mathematics and other disciplines. So it's a way that can be used to model various real life situations, like, for example, the financial status of a gambler, or things like the path of a molecule in a liquid or a gas, or the search path of a foraging animal, and a whole bunch of other things. Take a look at this Wikipedia article, which I'll link to, and take a look at all the applications, including sculpture making, or physics, or brain research, and a whole lot more. So once you're ready, go ahead and see if you can program your turtle to create a random walk using random colors. And I want you to think about how you can get the thickness of the drawing seen here. So each of the lines is a lot thicker than before, and also see if you can figure out how you can speed up the turtle so that it draws much faster. And everything is of course going to be in the documentation somewhere for you to find. Pause the video and complete the challenge now. Alright, so I'm going to delete all the code from our previous challenge, but I'm going to keep my list of random colors, which I'm going to use for my random walk here. Now I'm going to keep the random import even though it's currently unused, because as you guessed it, a random walk is going to require some randomness. So how do we actually get our robot to move in the 4 different directions? Well, let's define another list called directions. And this is going to have all of the different directions the turtle can face. So we'll start from 0, which will be facing east, and then 90, which will be facing north, 180 will be west, and 270 will be south. So now that we've got these random directions, we can get Tim, our little turtle, to start moving. So every time we're going to move forwards by the same distance. And it doesn't really matter how far you move your turtle, as long as you set a reasonable number. So I'm just going to choose 30, and then I'm going to get my turtle to turn in a random direction. So I don't want to just use right all the time. So you can use left or right and pick a random direction from the list, but alternatively, you can actually use this set heading. So for example, we can set it to those 4 directions. all we have to do is call set heading and then pass in one of those angles. That's what we're going to do here. We're going to use the random module and the random choice method to pick a random direction. So now this robot is going to move forwards and then it's going to turn a random direction. But of course we want this to loop a few times. So let's say that we get it to loop 200 times. I think that should be enough to draw a decent sized image. Let's set the range to maybe 200 times for this loop to run. I think that should get us a decent image. Now, if you chose 300 or 500 or whatever other number, it doesn't matter. As long as you can get a decent image on screen, then it's perfectly fine. So we've now satisfied the basic constraints of a random walk. And you can see our turtle is now wandering around this alleyway completely aimlessly and modeling a real life process, like an animal that's hunting for food. Now let's implement the next part of this. Let's go ahead and change our code so that it generates a random color for each step. That's pretty simple because we did it before in the last lesson. So we're going to get Tim to change his color and we're going to use the random module and the choice method to pick from all the colors that we've already got in this list here. Now that it's pretty much random colors, random walking, the next thing we want to do, if you saw my demo of it, is we want to make each of the lines a bit thicker. So how do we do that? Well, we have to head back to the documentation. So it's probably going to be one of these methods. And if we just read through the names of the methods, they should give us a bit of an indication of which one might be the one that we want. If we take a look at the drawing control for our pen, you can see there's a method called pen size. And you can call this either pen size or width, but it does the same thing. Essentially, it just sets the size of the pen which the turtle draws with. If we set the pen size to something a little bit wider, say maybe 15 in width, then you can see when our turtle draws, it's now a lot wider and it's a lot easier to see what it's doing. Now, the final trick I want to show you is how you can speed up the turtle's animation. So if I was to wait for it to finish drawing here, that's perfectly possible, but I can also speed it up by tapping into the speed method for turtle. And I can either specify this speed as an integer or as a string. So the strings are fastest, fast, normal, slow, slowest, and this determines the animation speed of the turtle as it draws. So I'm going to go for fastest. So we can say tim.speed and we'll put in that string fastest. And now when we run it, you can see it animates way faster and it's drawing at the speed of light. Our little turtle is completely going nuts. But this means that it'll take much less time to complete our 200 cycles as we requested. So I hope you enjoyed this lesson and you managed to get your turtle to do a random walk. Now, many of you would have done this challenge and you might have thought, wouldn't it be nice if I could generate a completely random color rather than just selecting a random one from this list? Well, we can do that. And I'll show you how in the next lesson. So in the last lesson, we saw how to create a turtle that does a random walk. Now in this lesson, I want to show you how you can create a random color for your turtle drawing rather than just using the named colors and then picking a random one out of the list. When you take a look at the pen color of the turtle, you can see that you can use a color string, such as what we've been doing, using red, yellow, or a hex string that represents the color, or we can use a RGB color. And the RGB color is going to be represented by a tuple of different amounts of red, green, and blue. So what exactly is a tuple? Well, a tuple is a data type in Python, and it looks like this. It has round brackets around it, and then each of the items inside are separated by a comma. So does this remind you of another data type? Does it not look a little bit like a list? Well, indeed, a tuple is very similar to a list. Each of the items that go into the tuple are ordered. So let's pull up my Python console here, and let's create my tuple, which is denoted by a set of round parentheses. And then let's put in 3 items, 1, 3, and 8. And there we have created a new tuple. Now, in order to get hold of any of those items in there, I can write the name of the variable, and then using square brackets, I can access the index. So 1 is going to be at position 0, 3 is going to be at position 1, and 8 is going to be at position 2. So if I hit enter on this, then you can see that's going to be equal to 8. And if you click this drop down on the right, you can see the same representation, position 0, 1, 2, and those pieces of data, and the total length is 3. So at this point, you might be asking yourself, well, I already know about lists, so why do I need to know about tuples? What's the difference anyways? Well, a tuple is going to be carved in stone, so you can't change the values like you can with lists. For example, if I wanted to, say, get hold of my tuple, and instead of the 8 at position 2, I want to change it to 12. Now, if I go ahead and hit enter, you can see I get an error, and this is a type error. This particular type, tuple, does not support item assignment, so I can't just change it willy-nilly like this. And I also can't remove items from the tuple. I can't change it in any way. Once you've created your tuple, you can consider it as carved in stone, and it is what we call immutable. It cannot be changed. So why would you use a tuple then? Well, think about the times, like say if you're creating a color scheme for your website, or you're creating some sort of list that you want to stay constant, and you don't want somebody to accidentally change it or accidentally mess it up. Well, then you might want to consider using a tuple. And if you find yourself creating a tuple and then realizing, oh, actually, I need to change it, well, then you can simply put your tuple inside a list like this, and you can actually convert it into a list. Coming back to our documentation, the color is represented by a tuple, because if you define a color, you're unlikely to change it. And then we have a R, G, and B, which is in the range between 0 and the color mode. So the mode can be between 0 and 1 or 0 and 255. In the course resources, I've linked to this really handy RGB calculator tool, which demonstrates how RGB colors work so perfectly. You can see that if we have 0 amount of red, 0 amount of green, and 0 amount of blue, we get black. But if we mix different amounts of red and different amounts of green and different amounts of blue, then we can get all of the colors in the rainbow. The 3 primary colors can create any color that you dream of. And each of these sliders, you can see, goes from 0 all the way up to 255. So more red, more green, or more blue. And this is what the RGB color ends up looking like. I find it easier to think about the range between 0 and 255. So in Turtle, we actually have to change the color mode to 255. So to do this, it's a little bit tricky, which is why I didn't want to put this as part of the challenge. But we have to tap into the actual Turtle module and not the Turtle object, and then change the color mode for that module. Back in our code, we can tap into our Turtle module, which is known as T in our code. And then we can tap into the color mode to make it go from 0 to 255. So now that we've changed the color mode, we can now create a random color. So let's get rid of this list of colors. Instead, I'm going to create a new function called random color. And this function is going to return a random color using RGB. So let's first create a random red. So we use the random module and then use the randint and then generate a number between 0 and 255. And then we can repeat this process for the other two color spaces. So green and for blue. Now we've got three random numbers, one each representing each of the color spaces, and then we can generate our tuple. Here's a challenge for you. See if you can return from this function a tuple that consists of the three random integers, r, g, and b, and then use that random color to color the turtle drawing instead of this broken code which relied on that previous list of colors. Pause the video and see if you can complete this challenge. All right, so we know that to create a tuple, we need a set of round brackets or parentheses, and then we're going to put each of these in order, so R, G, and B. So here's our tuple created, and this is basically our new random color. And then this function is going to return that random color as the output. So now, instead of using random.choice and using that previous list, all we have to do is get hold of a random color that's going to be outputted from this function and then use it to color Tim's drawing. So let's run this code again, and you should be able to see that in this random walk, the color is completely random. Pretty much every single turn is going to draw something completely different in terms of color. And this is achieved by learning a little bit about how colors work and how we can generate them using the random RGB colors. Now, the final challenge for today comes courtesy of a childhood toy that you might have already seen. So this is going to be our training bike, and it's going to be the last coding exercise before we tackle our final project. So what are we doing? We're making a spirograph. Do you remember those geometric gear-shaped things which you would draw and it would make these funky circular shapes? Well, that's what we're going to be doing, but with Turtle. We're going to get our turtle to draw a number of circles, each with a radius of 100 in distance, and once it's done, we should end up with something that looks like this. So we're going to be using our random colors, and we're going to be using the documentation. I want you to dig through the documentation and see if you can figure out how to draw a circle and to determine how large the circle should be. And then I want you to figure out how you can get it to repeatedly draw a circle and change the tilt of the circle by a little bit each time so that you end up with that effect. Pause the video and give that a go now. All right, again, we're going to be scrolling through all of the available methods, looking for something that might help us. I think it's going to be somewhere in the Turtle Motion Move and Draw section, and if you look down this list, you can see there is a method that allows us to draw a circle with a given radius. So we can put in the radius as one of the inputs and draw our circle. Heading back to our code, I'm going to delete some of the previous parts where we've got the directions and also changing the pen size. I'm going to leave the speed as fastest because we're going to need it to go pretty quick to draw all of those circles. And I'm also going to delete the final for loop. Now, notice how I've got this warning here telling me that it doesn't really like the idea of me calling a variable the same as the name of a function. So why don't we just call this color instead, and then we can return that as the output and get rid of that warning. Now we're ready to code up our spirograph. So the first thing that we're going to try and do is to draw a circle. Now the circle requires a radius, so I'm going to give it a radius of 100, and when I hit run, we can see briefly that it painted a circle. So let's go ahead and create our screen from t.screen, and then we can use that screen.exitOnClick method so that when we run our code, it doesn't actually remove the window until we click on it. So I can see that I've painted my first circle, and I would like, if possible, to make my circle have a different color each time. So I'm going to change the color to use a random color that's produced by this function. So now every time I run my code, you'll see a different colored circle. The turtle is basically going to draw out this path and then go back to its original position facing east. If we wanted multiple circles to overlap with each other, then we're going to have to change the heading or the pointing direction of our turtle. If we look at this section, the current state of our turtle, you can see that you can get the current position, the current y coordinate and x coordinate, but you can also get hold of the current heading, so which direction it's pointing towards. And all we have to do is just call this heading method. So now if I print my tim.heading, then you can see that when I run my code and I take a look inside the console, it's pointing at 0.0. So what if we could change the heading to make it a little bit shifted? Well, there's actually a different method for changing the heading and getting the heading. For example, if we want to set the heading, then we have to use this method and give it a number. So what if I get the current heading and then maybe I add 5 or 10 degrees to it, and then I change my turtle's heading using set heading to the current heading plus 10. And then we get a new circle drawn. So let's see what this looks like. And you can see that I've drawn one circle and then I've tilted to the left a little bit and then drawn a second circle. So extrapolating this, you can imagine that if we had a loop that kept going, then we could draw our final spirograph shape. Let's create that loop. So the parts that don't need to be in the loop is setting the speed, but the color needs to change each time, the circle needs to be drawn each time, and the heading needs to be updated each time. Now I'm going to simplify this line of code to contract it into a single line. So I'm setting Tim to a new heading, and that is from the current heading plus 10. So now let's create our loop, and let's say we're going to loop 100 times. Now let's run our code and see what it looks like. You can see it's drawing out our spirograph. It's not as dense as it previously was, but look at what it's doing. It's drawing the same circle on top of a previous circle because it doesn't know when to stop. It's stopping only once it's gone through the 100 rotations. So how can we figure out a way to get it to only draw as many circles as we need? Let's say that I created a new function called drawSpirograph, and this function accepts a single parameter, which is the size of the gap. And that is going to be the size that's going to be in between each of these circles that gets drawn. And that's of course determined by the direction heading of my arrow. So if I pass in this size of gap, I'm going to use it here to change the tilt of my circle. But I can also use that, because it's a degree, to determine how many times my spirograph needs to be drawn. So we know that there's 360 degrees in a full circle. And for each circle that we're drawing, we're basically giving it a different offset, right? And that's our size of graph. So if we divide 360 by each offset, then we'll repeat our code for as many times as we need to draw all the circles and complete the final spirograph. Now, the only problem is if I call this method dar, I think I meant to write draw. So draw spirograph, and I give it a size of 5, so a little bit smaller than last time, tilting a little bit less each time. You can see that if I run this code, we get an error. And the error says that the float object can't be used as an integer, and it's telling us where we have that float object. So remember that this number is going to go into here, and then 360 divided by 5 is actually going to give us a floating point number, even though it divides cleanly, just because this is how division works in Python. Now, unfortunately though, our range function is going to need a whole number, an integer. It can't take a floating point number, because then how many times are we repeating it? 3.4 times? What does that even mean? So this input has to be a whole number. So let's turn it into an integer by creating an integer and then wrapping this calculation inside the brackets. So now when we run our code, you can see it paints our spirograph, shifting by 5 degrees each time. And once it's gone through all of the iterations and the spirograph is complete, then it actually stops. Did you manage to get the solution for this challenge? If not, be sure to review this lesson and fix your code as needed. Once you're happy with everything that we've explained so far, then it's time to head to the final challenge. Let's go ahead and create a $1 million painting. So for all of that and more, I'll see you on the next lesson. This might seem a bit of an odd question, but have you ever been to an art museum and looked at the exhibition and thought to yourself, I think I could probably do this, and don't really understand why it's considered art? Well, this is a piece of art by Goldschmied and Chiari called Where Should We Go Dancing Tonight? And it's meant to be a piece of concept art. But when the museum cleaners came here at the end of the day and looked at this mess of cigarette butts and shoes and random bottles, they thought it was rubbish, and they promptly cleaned everything up. So this is what the exhibition looked like after the cleaners were done the next day. So to the museum's horror, their star exhibition gets cleared up and mistaken for rubbish. So I was talking to a friend and I said, well, you know, a lot of these modern art pieces, I could probably do it, right? We could probably get together, put some bottles on the floor, make a mess, call it art. And he told me, actually, no, you can't. And you should read this book called The $12 Million Stuffed Shark. And it talks all about the economics of contemporary art. And it's a fascinating read. I've learned so much more about how contemporary art is priced and why they're priced the way they are. But it also led me to discover some pretty big, shocking discoveries. Like, for example, the art piece that's referred to on the cover of the page is this shark. It's a shark that was fished off of the coast of Australia, and then it was preserved in formaldehyde. But it was preserved really badly, like they didn't use enough chemicals, and the shark started going a bit green and a bit of grey in other places, and it also started molding. But this moldy green shark was bought for $12 million. And this is not even the craziest piece. So, for example, this diamond-encrusted skull was reportedly sold for $50 million. And these butterfly wings, which have been dissected and stuck to a canvas, was sold for $8.5 million. So who exactly is this crazy man who's creating all of these pieces of art that's fetching these insane valuations? Well, it's a guy called Damien Hirst. And I think out of all his paintings, the craziest ones are the spot paintings, because it's literally spots of color that are organized randomly on a page. And check this out. This particular piece was sold for a whopping £1.275 million. So maybe like $1.5 million. It's insane for a painting of dots. But what I thought was even crazier is if you look at this painting, at least it's got quite a few dots, right? You're getting your money's worth of dots. But look at this one. This is the same artist, Damien Hirst, and this painting, I counted, only has 25 spots. And this sold for £500,000. It's not even about the number of spots. So I personally still, as you can see, can't really work out contemporary art. But what I can work out is how to get Python code to crack Damien Hirst's color palette and use those colors to generate a random canvas of spot paintings that look equally, if not more appealing than some of the original Damien Hirsts. So this is what we're going to be making as our project. And we're going to be using that package Colourgram to get hold of the color palette. And then we're going to use those colors to create our own spot painting that's going to look like this. Firstly, we're going to be using a package called Colourgram. And Colourgram is a library of code written in Python that lets you extract colors from images. So, for example, if you take a look at this picture, once it was run through Colourgram and 10 of the most common colors extracted, you end up with a palette that pretty much looks the same as the colors in the image. This is the example of how you would use this Colourgram package. And in this case, they're extracting 6 colors from an image. So it basically takes 2 inputs, an image and the number of colors. If we go into Google image search and we search for a Hirst spot painting, you can see that there's a lot of spot paintings that this guy created. I want you to pick a painting with a color palette that you like. Maybe something like this, or maybe a bit brighter like this one. But essentially, pick one of these images and then go ahead and download it. So save image. And then you're going to save that image as image.jpg, so JPG. And then go ahead and hit save. Now go ahead and create a new PyCharm project. I've called mine Hirst Painting. You can call yours whatever you want. Now we're going to drag our newly downloaded image, image.jpg, into this project folder, Hirst Painting. And it's going to ask you whether if you want to move the file from, in my case, the downloads folder to my Hirst Painting project. So then we're going to agree and click refactor. So now this painting is inside my Hirst Painting project, and I'm ready to go ahead and create a new file called main.py, which is what I'm going to use to extract the colors from this image. Here's a challenge for you. See if you can figure out how to use this package Colourgram using their project description here and using the example code. What you're aiming for is to be able to print out a list of all the colors extracted from the image and each item in the list to be a tuple that you create. So remember previously we saw how the turtle module likes to work with color tuples, which are created with an amount of red, the amount of green, and the amount of blue, all contained inside a tuple. This is the format that you're going to try and get your data into. It might take a little bit of wrangling and a little bit of thought, but just before you get started, here's a quick heads up. I noticed that when I was testing this on Replit and when I searched for Colourgram in the packages, I couldn't actually find the package to install into the project. So this is another good reason for using PyCharm. It just gives you all the professional tools and it has access to all the things that you need. So pause the video and complete this challenge. Alright, so we know that in order to use external packages, ones that weren't installed with the Python standard library, we have to first install the package. To install a package, we go to our preferences and then we select our project and then we go to our project interpreter. Now we click the plus button and we search for Colourgram and there it is. Now let's go ahead and install the package. And once that's installed successfully, then we can close all of this and click OK. Now that we've got our package, we can actually import it. So we'll import Colourgram and we can use the method that's described here called colourgram.extract in order to get a hold of 6 colors. Now, if we want more colors, for example, in this image, there's probably a good 30 colors. So let's go ahead and extract 30 colors from this image. But of course, our image is not called sweetpig.jpg. Ours is actually called image.jpg. So let's go ahead and rename this image so that it matches with our file. And remember that your image has to be at the same level as your main.py for this kind of code to work. So make sure that you've got it inside the Hearst Painting project folder on the same indentation level as main. Now let's go ahead and print out our colors that are generated. And remember that when you hit run, this process might take a little while. And the author of the library says that for a 5x12 by 5x12 image, it takes about 0.6 of a second. Obviously, if the image is larger, it'll probably take a bit longer. Let's go ahead and hit run and see what we get. Once the process is finished, you can see it's created some colors, and these colors are in a list, and it's got some different formats for the color. To understand that, we have to go back to our documentation. You can see that the color that's extracted can either be a RGB color, which is what we're interested in, or an HSL color, which is not quite what we want. So let's go ahead and write a for loop that taps into each of those colors. So for color in colors, let's go ahead and create a new list called RGB colors, and we'll just leave it as an empty list. And then for each of these colors, we're going to add to our RGB colors by appending. And the thing we're going to append is each of these individual color objects, and then we're going to get the RGB value. And once this process is done, then let's go ahead and print our RGB colors. So now you can see we've got a whole bunch of RGB colors with R equals what, G equals what, and B equals what, but this is not quite the format that we needed in order to use it inside the turtle. We actually have to go one step further. We have to create a R, which is from the color.rgbcolors.r, and then we repeat this process for green and blue. And then we create our tuple by creating our new color, which is going to be equal to a tuple with a parentheses and then R, G, and B. Finally, we're going to add to our RGB colors by appending this new color. Now let's print our RGB colors. And you can see we've finally got it in the format that we need. A tuple with the R value, G value, and B value that we can use in our project. Now we've managed to get the first part of the problem solved. So we can go ahead and copy this entire list and paste it into our main.py. I recommend actually testing out these colors using the W3 Schools RGB tool. Go ahead and paste your color to replace this current tuple here. Make sure that you still got that word RGB there, and then hit enter, and it will insert each of these values into the R, G, and B. So you can see the first color we got is actually a shade of white, so probably one of the backgrounds. So we can go ahead and delete that one because we're not going to be painting the background in our dot. It's just going to be white. Now let's check the next one. As you can see, the closer the numbers are to 255, the more likely it is that it's a shade of white. So this one is probably one of the other background colors in this image. So we can delete that one as well. And finally, this last one is probably going to be also quite white-ish. And we can probably delete that one too. This one, because of the blue, that's 109, I'm gonna be pretty sure that this is actually a real color. And there we go, we get this kind of sand color, which looks very similar to some of these colors that we see on here. So we can presume that the rest of these, because they're sampled by the frequency of occurrence, are probably going to be real colors that we can put into our painting. Let's save this list as our color list. And we can comment out the rest of this code because we don't need to run this computation every single time. We just want to extract the colors, and then you can delete or comment out the cologram related code. In the next lesson, we're going to be using this color list to create our Hearst painting. So for all of that and more, I'll see you there. Now that we've used cologram to extract all of the colors from our image, and we've created a list from that extraction, and we've gotten rid of all the white shades, then we're now ready to go ahead and start using this color list to create our Hearst painting. So you can either delete the rest of the code or leave it commented out, but the goal of the challenge is to use Turtle and those colors that you've just extracted to create a spot painting like this. Here's the requirements of the program. You're going to paint a painting with 10 by 10 rows of spots. So that's going to be 10 along this side and 10 along this side. Each of your dots should be around 20 in size and spaced apart by around 50 paces. So you're going to need to look at the documentation for Turtle to figure out how to draw these dots. You're going to have to figure out how to move your turtle so that it creates this 10 by 10 pattern and paint our 100 dots using the color palette that we generated. This is your chance to shine, and it's time to pause the video and complete the final project. So the first thing we're going to do is we're of course going to need to import our turtle, and I'm going to give it an alias just to make it more clear what it is that I'm referring to. I'm going to create my turtle, which I'll call Tim again, and it's going to be created from the turtle module, and inside there's a turtle class. Now that we have our object created and saved inside Tim, we're ready to go ahead and do some things with this turtle. If you take a look at the documentation for Turtle, you can see that instead of just drawing circles or just moving forwards or left or right, you can also draw a dot. Now, a dot takes two parameters, its size and its color. So we mentioned that we were going to draw a 20 size dot, and then we're going to pass in a random color. So let's create our dot. Let's say Tim dot dot. And then let's give it a size of 20, and then let's give it a random color. Now, because we're using the RGB color that has the R, G, and B values between 0 and 255, we first have to get the Turtle module to change its color mode to 255. And we saw this in previous lessons already. So now we can go into our color list and pick a random color using the random module. So let's tap into the random module and get hold of the choice method and pass in our color list. So now it's going to choose a random color from that list and then create a dot, hopefully. Now, we don't want our painting to disappear once we hit run, because right now, if I run this code, you can see it paints a dot and then it quickly flashes away. So let's create a new screen object from the Turtle module, and the class is called screen. And then we can get our screen to change its behavior by calling exit on click. This way, when we run our code, you can see our dot painted, and then only when we click does it disappear. So we've managed to get our first dot onto the screen. The next step is figuring out how we can get this process repeated. What if we get our Tim to move forwards by, say, 50 paces, and then we draw another dot? So let's put this into a loop. Let's get it to run 10 times. And then let's indent this block so that it goes inside the loop. And now our turtle is going to draw 10 dots. But notice how it goes off the screen and it kind of starts bang in the middle. And there's also other problems, like we're drawing the path as the turtle is traveling. Let's address one thing at a time. Let's try and move our starting dot so it starts somewhere down here. Now, there's quite a few ways of solving this. One way is simply by turning our Tim, the turtle, before we go into the loop and setting its heading so that it points in this direction. You can have a play around with the heading, and through my experimentation or playing around with the code, I've realized that I need to get this heading somewhere between 180 and 270. So what's halfway between 270 and 180? Well, it's going to be 225. So let's change our heading and let's try again. And you can see that our turtle is now moving roughly in the right direction. So we know that each time the turtle moves by 50. So if we want it to start about here-ish, then we need to move it 1, 2, 3, 4, 5 times. So 50 times 5 is 250. So we'll set our heading for Tim, and then we'll get him to move forwards by 250 paces. So that way we get started right over here. Now, at this point, it's still going to be pointing in that direction that we set over here. So we'll have to set the heading back to 0 if we want it to continue in this direction. Now, at this stage, you might realize you need to do a little bit of tweaking. So we could maybe move our turtle forwards a little bit more, so that it starts around here and we get enough space for our dots. But the next important thing we need to solve before we get rid of the lines, because we can still see the path of our turtle, which is really helpful, is we need to figure out how to get the turtle to turn left, move up by 50, turn left again, and then start creating the second row. That means we need to turn Tim so that it faces up, which is a heading of 90, or you could also just turn it left by 90 degrees. And then we're going to get it to move forwards by 50 paces. And then we're going to get it to turn left again. So we'll set the heading to 180, which is facing left. It's through these stepwise changes to your code that you can actually get a good sense of what it's doing, because you can see it drawing and then see if it's doing what you want it to do. Now, we know that we have our for loop, which is able to draw a line of dots going from left to right. Why don't we move our turtle so that it starts out here again, and then it can move along and create another line? So after turning it to the left, we're going to get it to go forwards by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, by 10 times 50 paces. So that's going to be 500. So now the final thing we need to do is to change its heading so that it faces right again. And now we're pretty close. All we need to do is to get this to repeat every single time we draw 10 dots. How can we do that? Well, firstly, this needs to go inside the for loop. Well, let's say that we create a new variable called number of dots, and we set it to 100. We're going to use that instead of the range. And we're going to create a range from 1 to the total number of dots we need to create. And then we can replace this underscore with an actual variable that we'll use inside the for loop. So we'll call it dot count, because this is going to represent the current number of dots that have been painted. Now that we've got the dot count, we can then go ahead and use an if statement to check and see if the dot count modulo 10 is equal to 0, then this means that the dot count is either 10 or it's 20, 30, 40, 50, 60, 70, 100. And under those circumstances, we want our Tim to move so that it can go to a new line. So now if I run this, you can see that Tim draws one row of dots and then swings back around, start at the beginning, and draws another row of dots, and then keeps on repeating this until it gets to the point where it's drawn 100 dots. But this is obviously very slow, so we could speed things up a little bit by changing the speed of Tim at the very beginning to fastest. So this way it'll animate a lot quicker and we can see our dots show up and it takes a little bit less time to see it in action. Once our painting is completed, you can see there's one other bug. Our final dot is not painted. And this is of course because our range operator goes from 1 to 100, and that means it's only going to run 99 times because 100 minus 1 is equal to 99. So we can add 1 to this. So once we've changed that, then we manage to get our 100th dot, which of course again triggers a new line. Now, a lot of these lines were really useful when we were trying to visualize how our turtle is moving. But now that we've got our painting in place, we need to try and get rid of these lines. So we know that from the documentation, we can use pen up and pen down. At the very beginning and the moment where we've created Tim, we can already get the pen to come up so that we don't draw those lines that you see. By drawing dots, we don't actually need the pen to go down. It's just going to leave a dot and then move on. So just by writing pen up and no pen down, we already get our dots being drawn. Now, the very last improvement that I can think of is once our painting is completed, I'd really like to get rid of the shape of the turtle, which in our case is a little arrow. Now that's really helpful when we're trying to figure out which direction it's facing or how it's moving. But at the very end, we don't really want this. So again, back to the documentation. How can we get rid of our turtle? Well, there's show turtle and hide turtle. And this is how we make the turtle invisible. It even tells us that you can do this while in the middle of a drawing because hiding the turtle will speed up the drawing observably. So let's go ahead and hide our turtle as well as moving the pen up. And let's re-visualize this. And you can see our dots being drawn without our turtle. And we end up with a beautiful Hirst painting that we've created completely from scratch. Well, maybe with a little bit of help from Damien Hirst's color palette. So I hope you enjoyed this project and I look forward to seeing you tomorrow.